There are another couple of terms that you will come across whenever you are working with magnetics, and that is permeance as one of the term. Another is reluctance. They are very well connected, and let us see what this permeance and reluctance means. Let us start with the basic equation B is equal to mu H. This is coming from the BH characteristic for the material. Flux density is equal to permeability mu into H field, Ni by Lm. So let us replace flux density by flux by area of cross section, flux density, and this mu into H is Ni by Lm, magnetic path length. It can be written as mu by Lm into Ni is nothing but MMF. So flux can be written as mu into AC by Lm into MMF. This term here, mu permeability into area of cross section by the magnetic path length, is called permeance with this uppercase lambda here. So it's called permeance, and therefore flux is equal to permeance into MMF. This is one important relationship. It is as important as Ohm's law in the electrical domain. This is also written slightly in a different manner. There is another term called reluctance which is frequently used, and it is defined basically as 1 by permeance, inverse of the permeance, and therefore this becomes reluctance is equal to Lm by mu naught AC, mu AC. Now if you reframe this, you will see that phi is equal to MMF. This portion comes into the denominator into reluctance. So phi is equal to MMF by reluctance. This is also a popular way in which the phi flux and MMF are related. In fact, in many of the literature, sometimes people confuse this with the Ohm's law or in the electrical domain and call this as current. This is the potential, and this is equivalent to the resistance. Reluctance is not equivalent to the resistor. Reluctance is not a dissipative quantity, and phi here is not a kinetic term. d phi by dt is the kinetic term, as we saw. To conserve both the units and power, it is d phi by dt which is the kinetic term in the magnetic domain, and MMF is the potential term. So let us try to understand this a bit further. We know d phi by dt. d phi by dt we know is the kinetic term or the kinetic variable in the magnetic domain, and it is same as the kinetic, it is similar to the kinetic term in the electric domain, which is current I. So if I integrate both the kinetic terms, integral of d phi by dt with respect to time and integral of I dt with respect to time, what do we get? We know integral of I dt is nothing but charge, am second. So this term is nothing but charge q. And what is this term? d phi by dt integrated with respect to t is nothing but integral of d phi, or which is nothing but phi. So this is phi, or the flux. So if you see the phi, the flux is linked more with the charge in the electrical domain. You substitute there in this equation, you see how well they fall in place. Now for phi, I will replace it with charge q, and with permeance, I will put it as C, and MMF is V. Q is equal to CV. This is a well-founded relationship in the electrical domain, and you see the equivalent relationship in the magnetic domain. Phi is equal to permeance times MMF. So permeance is actually behaving like equivalent to the capacitance, and in fact it is so. In fact, the energy storage within the magnetic domain is happening in the permeance. It is happening in the equivalent capacitance in the magnetic domain. So what is reluctance? Reluctance is 1 by capacitance and nothing but elastance. Normally the permeance is a much more visualizable term than the elastance. So elastance is 1 by C. We will be using permeance and the term reluctance in our design of the magnetics frequently. Therefore, let us just expand these terms a bit more. Let me draw the BH curve, straight line like this, and the saturation parts. Now this is the BH curve of a core. Now what will be the BH curve of free space? No core in it. So the slope will be very, very low, almost horizontal, but I will show it zoomed with a finite slope like this. Now this is the character of free space and it has a value mu naught. We'll call that one as mu naught, the permeability of free space. And it's a constant. It is 4 pi into 10 to the power of minus 7. It has a units Henry per meter. Now this is a constant, universal constant. It is the permeability of free space. Now the moment I introduce a core, you will see that the slope jumps to a very high value, and that is mu. Now this mu is having mu naught, slope of free space, into some correction factor mu r. Mu r is the relative permeability. It is a numberless quantity. It is a unitless quantity. It is just a number. So this for ferrites varies normally between 2000 to 2500. What it basically means is that if this is the slope of free space, the slope of the BH curve in ferrites will jump by a factor of 2000 to 2500, and therefore it becomes almost vertical. So this is the relative permeability. So mu is having two parts, the permeability of free space and that of that constant part, or a unitless part, which is a scaling factor which scales the free space permeability to get you the permeability of that in the core. So now if you take this equation phi, which is equal to permeance into MMF, permeance is given by mu A by Lm. That's what we saw here. Permeance is nothing but mu AC by Lm, and mu gets expanded into mu naught into mu r. Mu naught, that of free space, 4 pi into 10 power minus 7 into mu r, relative permeability of that particular core which you are going to use, area of cross section of the core by the mean magnetic path length Lm for the core. Likewise, the reluctance is 1 by permeability, which is Lm by mu AC, as we saw here, and mu can be expanded Lm by mu naught mu r AC. So this is the relationship between reluctance and the core cross section permeability and the mean path length, and so also between permeance and the core cross section permeability and the mean path length.